Good afternoon, students. I am at Nalanda Lectural Complex in room number NC411 and offering today's lecture in hybrid mode. So those of you who are joining online, they can see my screen, and also those who could not join, for them the recording has been started, which will be available for those who are not able to attend the class today live. So with that background, let me start today's lecture. And as you can see that this is chapter 12 on query processing. And also this is the very last topic of our course. And we will touch upon some of the more interesting concepts in query processing. So far, if you have seen that when we are writing SQL queries, we are doing a lot of select. We are primarily here, this query is talking about select type of queries. We have also studied various types of indexing techniques and storage. So all these were discussed, and the importance is that if we follow appropriate storage and indexing techniques, then when we try to execute certain queries, the result will be returned in an efficient manner. Also, if you see that we have done several operations there, we have done, for example, this group by and order by, and even without group by, we have order by and so on in SQL. So types of queries. So that is what we are going to cover today. So not all of the topics that we are going to mention will be required to be understood in detail, because there are many subtle points which you will be able to appreciate only when you are actually working in the database backend. Okay, so if we look at the basic steps in query processing, so we have a query, and then there is a parser and translator which maps it to relational algebra expression, and then this expression that we get, so that needs to be optimized. Now, what is meant by optimized? See, if you consider a table where we write, say for simplicity, select star from T1, where say salary is greater than 10,000 and department code equal to CS. Now you see that if we have this particular query and we have its relational algebra expression, and there we can have first the selection based on the department, and then the selection based on the salary, or we could do it the other way. Similarly, depending on which all indexing structures are built on that table T1, whether there is an index on salary, whether there is an index on department, whether there is no index on either salary or index, or whether there is an index on both salary and index. So these will actually determine whether we should first do the selection based on the salary and then also on the department, and not only whether such indexes exist, but also what are the different possible values of those indexes, what is the depth of those B plus trees, how many different possible values are covered by each value of the search key. So these are all very important considerations while determining which of those indexing structures should be used, or if at all any index should be considered while executing this query. So this optimizer, the query optimization, is a very important step. And as I said, that which value of the search key covers how many possible rows in the table. So these are what we denote here as the statistics about the data. And based on all such considerations, there is this very important optimizer piece of this query processor in the database management system. And remember that this optimization is a true optimization problem, a real life optimization problem, and that itself should be very, very efficient. You cannot actually have the optimizer run for 5 minutes and then determine which of the ways of carrying out the query execution would be the best, and then the execution takes less than a second. So you cannot let the optimizer be inefficient. So you have to have a very efficient optimizer, and which uses various data. And if it finds that the time it might take to actually optimize the query execution will indeed be pretty large, then it might just forget about doing any kind of optimization and straight away go for a full table scan of the data. So, but finally, this optimizer comes up with an execution plan and then an evaluation engine that will run that execution plan on the data and returns the query output. So this is very, very important slide that tells us the primary steps in query processing. Now, the query optimization, as I said, the relational algebra expression may have many equivalent expressions. So as I just now mentioned, that we have a projection on salary and then a selection on salary, and which is equivalent to first doing a selection on salary and then doing a projection. And this is about a case where we can interchange the selection and projection operations. But as I said, that there could be selection first on one of the attributes and then on another attribute and so on. So all these things are different possibilities for any given query as input and the corresponding relational algebra expression that we want to derive as the output. So each relational algebra operation can be evaluated using one of the several different algorithms. So correspondingly, a relational algebra expression can be evaluated also in many ways. So annotated expression specifying detailed evaluation strategy is called an evaluation plan. For example, can use an index on salary to find instructors with salary less than 75,000, as I was just now mentioning, or can perform complete relation scan and discard instructors with salaries greater than or equal to 75K. So you see that we can use the index, we may not use the index, and all these are part of query optimization. For example, here we consider, say, projection on salary and then the selection on salary less than 75,000. So this is what we meant here, that this annotated expression. So this is where we are annotating that this pi salary will not going to use any form of index, but this select operation on salary less than 75K. So this annotation is that it will be using index 1, and it is going to then execute on the instructor relation. Now, if we consider the various measures of query cost, so there are various measures. Remember that what we are showing here is a bit of an abstract representation of the same. So for simplicity, we just use the number of block transfers from disk and the number of 6 as the cost measure. So if you remember that when you have this platter and you have the head of the disk or the disk system, so what happens is that this head has to move and it has to be positioned on the appropriate track of the platter, and once it is on the appropriate track, then the disk has to rotate so that the appropriate sector comes right below the head, and then only you can make the access. So you have this time for seek where it goes actually to the right track on the platter, and once you have got the appropriate track under the head and also the appropriate sector, so the specific sector within the specific track is below the head, then what happens is that if now whatever you are trying to retrieve, they are all stored in adjacent such sectors on the same track, then what you need to do is that you just simply read one sector, transfer it, and then the disk can rotate a little bit. You go to the next sector. I mean, the next sector gets positioned under the disk head, and then you read from that sector and so on. So if all the data that you are going to read, they are all next to each other, located in adjacent sectors, and you don't have to move from one track to another, then you actually do not need that additional seek time to go to the appropriate track. But even then, there is this data transfer rate. So even if you can position the head, then with all the interconnects, the wires that you have, the wirings, using that, the data has to move from the disk of course, then to main memory, as you have studied, it has to go from the disk blocks to the buffer blocks. So that is what is the block transfer that is taking place. So there is this transfer time for one block and the seek time when it has to be positioned on the appropriate track on the platter. So so the cost for B block transfers plus S6 is S into TS, of course, plus B into TT. So we ignored the CPU costs for simplicity, but real systems have to take CPU cost also into account, and we do not include any cost to writing output to disk in our cost formula. Now, here we have listed a few types of possibilities, and we are just going to touch upon those points. So you can always go through those in detail in the books. We have mentioned the particular sections that you have to focus on. So one step or one requirement is linear search. That means you scan each file block and test all records to see whether they satisfy the selection condition. So if we have something like this, that salary less than 75,000, and we do not use any index at all, then we are talking about a linear search. So we are not using an index, just one by one we are reading on the blocks, and you can estimate the cost that if the blocks are all located in adjacent sectors, so you have one seek time and then BR block transfer. So if the selection is on a key attribute, so mind it, if it is on a key attribute, you will not be getting multiple such rows. So as soon as you get the correct block where that particular row exists, okay, and if it does not exist, then of course it has to go through all of them. And if it is the primary key, then if it finds a record, it knows that there cannot be any more record. So it will just have this one block transfer. But on an average, the advantage is that it is something that can be applied regardless of selection condition or ordering of records in files, availability of indexes, and so on. And you have a total bound on the time. Now, of course, that binary search does not make sense, because remember that binary search that we have all studied, these are all with respect to in-memory type of data, where you have the data already moved to memory and where you are doing binary search. But here in the context of this one, the binary search does not make sense, because you are actually moving from one disk block to another, and of course you are not going to get them in adjacent sectors. So that is going to cause difficulty. Now, when you have indexes, there are many different possibilities. As you can see, that index, it could be on a primary index, and you are trying to do an equality on the key. There could be primary index equality on non-key. So if it is equality on key, so that means that as soon as you get one record retrieved, you know that there cannot be any further record. But if it is equality on non-key, then of course you may have to retrieve many different such records. So these are the considerations that one has to have when we are trying to use the selection with the help of indexes. And say if you have a secondary index, now when it is a primary index, then what happens is that the actual data is also stored in the order of the value of that search key, which is constituting the primary index. And if you are only going to use the primary index and equality on the value of the key, then you get this result. If it is non-key, you get some results. Now, if it is a secondary index means what? Secondary index means the actual data, the ordering of the data in the different blocks in the sector is not going to be the same as the particular index, because when it is, as you know, that the data can be stored only in one physical order, then that of course makes sense, because you are not going to store the data in multiple different ways when you are storing in the disks. For example, if you have say the student table with roll number as the primary key, and if you are going to create index on it, so if it is the primary index, then it will be actually storing the data also in the physical disk in the order of the roll number of the students. However, if you have this roll number as the primary key, but you could always say that I'll create my primary index or clustering index, as it is often called, or clustered index, based on say name. In that case, of course, the primary key is roll number, but um, uh, the uh, the, uh, the the primary index, as you mentioned, that primary index A2, the primary index is on name. So you can have that option. The other option is that you have this primary index is on roll number. So the data is actually sorted in the order of roll numbers when it is stored in the database. And now you have defined an index on name. So now this name, the index on name cannot again be a primary index. It has to be a secondary index. And suppose you are trying to use that secondary index and you are doing an equality on non-key. So that means that you are going to have multiple matches. So in that case, you see that you have to actually compute. We don't need to worry about the exact formula, but it is very easy to figure out how these are coming based on the basic premise that we mentioned is that we are going to talk about the seek time and also the block transfer time. So based on that, we'll have these various costs that can be arrived at. Okay, and in the book actually we'll see that there are multiple such other possibilities. These by no means are the only possibilities. A4, so you could have no indexes, and then you are doing a equality on a non-key or equality on key and all such possibilities. So these are all different combinations of the availability of various indexes, and whether you are doing a search on key values, whether you are doing a search on non-key values, whether it is equality or it is a range search. So even for example, if you have say there is roll number as the primary key, you have defined a primary index on roll number, and then what you are doing is that you are now searching on a range of roll numbers. Okay, so these are all different possibilities which need not necessarily always be as shown here as equality on key or equality on non-key and so on. Okay, so what we are trying to emphasize here is that based on the type of indexes that you have, the type of search that you are having, then there are multiple different situations that can occur. And based on the situation that is occurring, you will have different measure of cost for executing this query. So when the query optimizer is trying to figure out which particular query plan to form, and as we have shown in this particular figure at the beginning, that this optimizer is a very important component of the database management system, and it has to use a lot of statistics about the data, that which index, even in the context that I talked about, that how efficient it is going to be for using one or more of the indexes that are available, or even carrying out the process of optimization itself is going to be expensive. So actually they use what is called cost-based optimization, that how much it is going to cost in order to come up with the most efficient execution plan. And as you have already seen now, that there are many different possibilities, and it is only talking about existence of maybe one index at a time. And also at the same time, we are making things simple, where we are saying that the where clause is using maybe only one column's values, whether it is equality on key, equality on non-key, or there is the range search. But as you can see that our queries can be very complex, where we are joining multiple tables, and they can have a mix and match of various types of indexes. And that's why people have come up with these concepts of join indexes and all those things. Uh, but this becomes very important. So if you are actually going to work in any database management system company like Oracle, and you are going to work on the development of the product itself, then definitely query optimization is one of the important steps in which they are always trying to improve things. So we can implement selections of the form, say sigma a less than or equal to r, or this a greater than or equal to r, using a linear file scan or by using indexes in various ways. So primary index comparison, as I said, that it is going to do a relation is sorted on A. So if you remember that in B plus tree indexes, at the leaf level, what you have is that in the leaf level, within a node also the search key values are sorted, and from one node to the next one, which are connected in a chain. So there also the values are sorted. So if you move from left to right, and if you are going to access those records, what will happen is that you are going to get them in order. So if you have a particular search key, which is a column or a combination of columns in the table, which forms based on which you have created the B plus tree index, and then you are doing a such range search, then what will happen is that once you go to the starting point, like if it is a salary between say 50,000 to 70,000, and if there is a B plus tree index on salary, then what you have to do is that you have to first go to the particular leaf node where the salary of 50,000 starts. But then if you from there, if you keep on moving to the right, you will get all the search key values which are say 50,000, 55,000, and so on. So if it is between 50,000 and 70,000, so what it will find is that, so those with 50,000 and then 55,000, 56,000, those could be in one leaf node, and then it has got a pointer to the next leaf node. So you have to keep moving till you get a search key value which is greater than 70,000, and then you know that that is where all your records are stored, because all these values are sorted. So you cannot have anything between 50k and 70k, either to the left of the entry in the leaf node which started with that 50k, or to the right of the entry in the leaf node that ended with 70k plus. Okay, so these are all sorts of possibilities, as I say, that there could be secondary index comparison and all mix and match. And once again, it was a simplistic situation when you have complex joins and you have subqueries and so on. So you can very well understand that it is going to be really expensive. And that's why, if you remember at the very beginning, when we talked about all these basic concepts of normalization, when you might go for denormalization, I was emphasizing the fact that more number of joins you have, the queries tend to become more inefficient. The one of the reasons is 3, 4, 5 tables, or they are involved in maybe subqueries to a certain extent. So what it has to figure out is that with so many different indexes possibly existing on those 4, 5, 6 tables, then which particular combination and in which order, not only the set of indexes to be used, but in which order those indexes are to be used. So figuring that out itself becomes very complex for the optimizer, and that's why we try to see if we can reduce the queries and so on. But of course, reduce the joins. Sorry, but of course, if your queries are complex, you will need actually need to carry out these types of joins and optimization. But the good point is that when you have this online transaction processing kind of environment where you are doing things online, like say our ERP application or a banking application that we experience, or a flight booking application, what happens is that there, you're most of the time you are not going to do query. Most of the time you are actually going to do multiple different tables, provided the table design is done correctly. The developers have not unnecessarily created and partitioned the same table in many different ways. If you remember, I emphasized that if there are two tables with the same primary key, then ideally it means that they could be kept together. Maybe you have to have certain null values and so on. But if not, then what you are doing is that always when you are trying to get the data out of those two tables, it will involve an additional join. So these are the points that we had mentioned before, and now we are trying to stitch together the concepts that we are discussing here. And then the very final topic also in this slide set is about sorting. Now you see that we talk about accessing the data, but once we have got the result set back, then we say that we will do a sort by, that is order by some say salary, or order by name, or order by roll number, and so on. So how does that sorting take place? Remember that when you are in talking in the database context, you have possibly millions and hundreds of millions of rows for real large systems. Now, if that is the case, then you are not going to have the entire data in main memory so that you can apply your standard known sorting techniques like quick sort or whatever. So when the data is not fitting in main memory, then how do you carry out the sort? So there is this technique which we are going to discuss. So which is called external sort merge, which people have found is a decent technique, and which actually keeps in mind that you only have a limited amount of memory which can be used for sorting, but your actual data containing hundreds of millions of um, elements which are not fitting in the main memory. So how you can do the sorting? So we are going to look at that external sort merge technique. So let us see the different notations. So let M denote the memory size, say in number of pages. Okay, so if you remember again that we can bring data from the disk to the memory in the buffer block. So those are like blocks or pages. And then how does it work? We create sorted runs. Okay, so what is meant by sorted runs? So let I be 0 initially. Now what we do is that repeatedly we carry out these steps. So suppose in the disk you have say 1 million. Let us take for simplicity say 1 million records. Okay, and then suppose you have say let us consider say 10 is the memory size in pages. Okay, so now each memory block, suppose it is for simplicity, it is say just I'm taking a number. So we have say each memory is of size 1000. So when you have 1000 means 1000 such data elements can be fit into one memory page. Okay, and you have 1 million. Okay, so and you can have 10 such memory pages in memory. So that means what? That 10 into 1000, at most 10,000 elements can be brought from those 1 million into the memory. So let me repeat the numbers again. So I have say 1 million data elements, and I have 10 m equal to 10. So I have 10 pages of space in main memory, and each can store up to 1000 data elements. That means out of those 1 million, I can bring in only 10,000 data elements at a time. And what happens? That these 10,000 data elements that we bring in, 1000 will go to the first page, next 1000 goes to the next page, and finally the 9000 to 10 or 9001 to 10,000 that will go to the 10th page. So that is what we mean here. In this example, we have m equal to 10, and memory size is we are considering that. So this m is the number of pages, that is the size of memory, and each page size I was taking the example of say 1000 elements. Okay. Now what you do is that once you have brought these 10,000 elements in main memory, you sort them as in memory blocks, because now you have these 10,000 data elements in memory. Now you can apply any of your standard sorting techniques like say quick sort for sorting those data elements in main memory. Now what you have in those 10 pages of memory, you have these 10,000 data elements which are now in sorted order. What you do is that these 10,000 data elements which are in sorted order, you write it back to the disk and you call that as a run number Ri. So let us consider I is initially 0. So you brought those 10,000 data elements out of 1 million in memory, sort them, and then you create run number brought into memory. Now you are storing them in the disk. Now what you do is that you now bring in the next 10,000 data elements from the disk to the memory, and you create the next run, which is R1. You store it in memory. So now if you repeat this whole thing 10 times, what you have created is that you have created 10 runs R0 to R9, each of which are individually sorted, but they are now back in the disk. So you have created these initial sorted runs, but now you have to merge them. Okay. So now you see that it is very similar to your notion of merge sort, where you have all these things actually broken down into pieces. It is a little different, and now you are from now bottom up you are going to put them together. But when you are putting them together, you are having each of those elements of or array elements individually they are sorted. So you are actually merging them in the merge phase of the merge sort, of the merge sort algorithm, right? Okay, so now we have to do the merging, but again, merging also you cannot do simply like what you do in merge sort, because when you talk about merge sort, we are saying that we are merging two arrays, right? Two sorted arrays. But we are never thinking that these two arrays could be too large not to fit in memory. There, we made that implicit assumption that they are all in memory and you are just merging. Okay. But here, the question is that you have these 10 runs that you created, R0 to R9, each of size 10,000. You cannot again now bring them all together in memory and sort, because it will not fit in. If it was possible, you would have done it in the first place. So we have to do this merge. This merge the runs, which is called n-way merge. We assume now that n is less than m initially. So use n blocks of memory to buffer input runs and one block to buffer output. Now let me explain it. What it is written is fairly simple, but if I give you the example, it will be very easy for you to follow. So now you see that I have these 10 such runs created. Okay. And now again, remember that I can have at most, as I said, this m number of pages, so which I took the example of 10 such, and each with 1,000. So what we do here, we now from and each run that I created, if you remember, we created 10 runs, but each of size 10,000. But each page in memory, in our example, can fit only 1,000. So what you do? You bring in 1,000 such elements from run number R0 to memory. You bring 1,000 from run number R1 to memory page 1. Okay, so from, if I number the memory pages from 0 to 9, okay, if assume there are 10, one I have to reserve for outputting things. So I now have only 9 such memory blocks, or what we call as pages, 0 to 8. Okay, so what we do, we, and let 8 runs. Okay, let us just sorry, we had only 9 runs. Just to make things simple, assume that there were only 9 runs created. So what you will be doing is very simply like this. So again, I made things simple, which is actually the first line that is written here. Merge the runs, n-way merge, and we assume n is less than m. So that's why I said that instead of 10 runs, let us assume that there are 9 runs R0 to R8, and you will understand why. Because now I have these 9 blocks in memory, and in each block I can bring the first 1,000 elements from the corresponding run. So from run R0, I bring the first 1,000 elements in memory block 0. Then from run R1, I bring the first 1,000 elements in memory block 1. And assume there are 9 runs, so from the 9th run, I bring the first 1,000 elements in memory block R8. Okay, so in memory blocks R0 to R8, I have brought the first 1,000 elements from the runs R0 to R8, and assume there are only 9 such. Okay, now once I have done it, what I will do is that now we are doing the merging, very similar to, now you are assume that it is a n-way merge as is written here. So in merge sort, you know, 2-way merge. So you do n-way merge. So now you are having as if these 9 arrays which are sorted, and you are trying to merge them. So what you will do, from the first you have the pointers at the beginning, and then you see which is the smallest, you take that, and you have reserved that one block in memory for outputting the reserve, for buffering the output. So there you put there. Then you see that which is the next one, very similar to your merge sort, the merge step of your merge sort, but that is a 2-way merge. So here n-way you are putting, and then the output you are not writing to the disk, you are writing to that output block in memory which you have reserved for outputting the data. Now once that gets filled up, you push it back to the disk. Then what happens? These are all sorted, truly sorted across all the data elements. So instead of 1 million, I consider little less. Okay. Okay. Now, if that is the case, Then what happens is that next you keep continuing. When the buffer block is output buffer is getting filled up, you flush it to the disk. And in the process, when the buffer where you are getting the data from each of those runs, the individual buffers, the memory blocks, say M0 up to M8. So if M0 is empty, you bring the next set of 1000 elements from the corresponding run, say R0, and then fill it. And then you proceed. So what you are doing is that from the runs that you had created, which are sorted runs, R0 to R9 or R8, as I said. So you are bringing the data in memory, you are doing NOA merge, outputting the value one by one in the output buffer block, and when that is getting filled up, you are flushing it to the disk. So that way what you are doing is that you are merging these things. So that is the merge step, which is the NOA merge. Remember that I made things simple, made n less than m. So I made n equal to 9, but suppose n is more. So n could be 20. So what you do is that first you have to do it for only 9. And all these 9, these individual runs of 9, these individual 9 runs, size 10,000. So what we have to do is that now what we'll do is that these are now longer runs, but number of runs is reduced. So from initially, suppose I had 20, so only 9 of them we can merge together. So then I will now have these 9 runs sorted and saved. Next 9 we pick up, we sort, save. Next 2 are left out of 20, we bring them, we sort and save it. Now what happened? I now have 3 runs, but each of longer size, right? Longer length. So now again I have to repeat the same thing. Now I have to only merge those 3 long runs. So you see that this way what you do is that you repeat it, and then finally we'll have everything set. So that is what is written here, that you repeat, select the first record among all buffer pages, write the record to the output buffer. If the output buffer is full, write it to the disk. Delete the record from its input buffer page. If the buffer page becomes empty, then read the next block of the run into the buffer, and until all input buffer pages are empty. If n is greater than or equal to m, as I said, that you have to, what we did here, you have to repeat it based from the longer runs that you generated in the each such pass. So in each pass, contiguous groups of m-1 runs are merged. Again, why m-1? Because 1 you have to store for outputting the result, the buffering the output, which will be flushed to the disk. A pass reduces the number of runs by a factor of m-1 and creates runs longer by the same factor. If m is equal to 11, then you see that there are 90 and there are 90 runs. One pass reduces the number of runs by 9. Okay, each 10 times the size of the initial runs. Okay, and you repeated passes are performed till all runs have been merged into one. So this is an example, as you can see, that if this is the initial relation, then in first go what we have is that, and remember that we are trying to sort it by the first column. Okay, so you see that we brought in this G24, A19 and D31 in memory. Okay, and then I could I could sort them, and then it was stored as ADG with A19, D31, G24, where ADG are sorted. Next, we brought into memory CBE. Those were sorted, and that run BCE that was created. Similarly, I created those other 2 runs. So now, after the first step, we have these 4 runs that got created. Okay, and then assume that you can only manage 2 runs together, okay, in the memory, plus 1 for output. Okay, so then this ADGBCE, so those are brought in memory, and then of course if you do the merging, here in this case it is 2-way merging, then you get this output as A19, B14, etc. So you see that the longer run got created, but within that run all the data elements are sorted. And similarly, separately DMRADP, so those are sorted, and those are again written back to the disk as longer runs, and then these 2 longer runs are brought. Of course, these longer runs you cannot bring everything together, so you have to keep bringing them in chunks. Okay, and you get this as the final sorted output. So this is something that is very interesting as to how actually large volume of data that cannot fit in main memory can actually be sorted. So this is just a simple calculation which is intuitive, that how many block transfers are taking place. So let BR be the total number of blocks containing the relation. The first stage reads every block and writes every block for creating the runs. So that will need 2 BR block transfers. And the initial number of runs will be what? It will be ceiling of this BR by N. Okay. So that will be the total number of such runs. Number of runs reduced by a factor of m minus 1 in each merge phase, which we have said here. So in each merge phase, we are reducing this by this m minus 1, by a factor of m minus 1. So now when we have to, how many merge phases you will need? You will need the ceiling of log of this BR minus M, that is the number of runs that got created, and then base M minus 1, because M minus 1 are merged together in one such merge stage. And each of these passes reads every block once and writes them once. And final pass may not output the list. So if we assume that the final block can and read the can stay in the main memory, so then one minus BR is only because of that one final step is not required. Instead, would return the result to the calling operation. So if we consider that, then we have the total number of block transfers is 2 BR plus twice this one. And even if we can make it simple that the final block is also written to the disk, then the minus BR will not be required. So minus BR is if the final block is there in main memory and it is returned to the user, then you are not going to write it to the disk, because it is only the output of a query that you are sorting. You are not storing anything in sorted order. So once you have the final buffer block where you have the data sorted, that can be returned to the user. So that's why that minus BR, but that is a simple thing. If you do not have that minus BR, you assume everything is written to the disk, then of course you will have this as the total number of block transfers, which is simply 2BR first, and then this is for 2BR is the for initial creation of the runs, and the middle term is basically for doing that merging of the sorted runs, and you can subtract that BR if you are not storing the final result back to the disk. So that gives us the total number of block transfers that will be required. Okay, so that brings us to the end of this chapter. So for this chapter, you need to focus on sections 12.1 and 12.4. And yeah, so that's all about this chapter. And with that also, we come to the end of our all the topics that we wanted to cover in this lecture today, and also overall in the course. So what we'll do is that we'll stop here for today, and what we'll have is tomorrow we will have the class at 10, and there we will summarize all the topics. So both Professor Ghosh and myself will be there, and we will wrap things up tomorrow. So I believe that it is not going to take more than half an hour to 45 minutes. So we'll have the lecture tomorrow, and that will be the final lecture for the course in this particular semester. So I am stopping the recording here.